Hello, good afternoon, everyone. Welcome to week 6 of this NPTEL course on applied optics. So, this is the sixth week, and we have come halfway through. This course is for 12 weeks, so we are at 6 weeks mark. And in this week, we have been introduced to the Febry-Perot interferometer. This is multiple beam interferometry. And also, we learned the terms related to Febry-Perot interferometer and coherence length, coherence time, uh, these properties also for any beam of light we studied. So this week, the questions would be focusing on Febry-Perot interferometer and coherence length, coherence time. Okay, before proceeding, let me provide the link to the YouTube channel for this course in the chat box of this Zoom meeting. So this YouTube channel is where you would find recordings of all the previous sessions. And all these live sessions that we have would also be live streamed on the YouTube channel as well. So if you face any network issues in this Zoom meeting over here, you could head over to the YouTube channel and watch it over there. Sometimes some people have mentioned that in Zoom things appear blurry, the audio is a little bit cracking. So in that case, I would recommend that you move to the YouTube channel and watch the video over there. Also, if you miss any session, then you could watch the recording of these live sessions on that same YouTube channel. Okay, so with that out of the way, let us get started with week 6 assignment problem. So this very first question is on Febry-Perot interferometer. Okay, so this first question over here says if the mirror reflectivity in a Febry-Perot interferometer is increased, then transmission peak becomes A, broader, B, no change, C, sharper, or D, none of these. So as always, I would launch the poll for you. Please submit the correct option in that poll. The poll appears on your Zoom screen. You would see a notification. Please take about a minute or two to answer the question. Okay, some people are asking where's the link to the YouTube channel. I believe you have joined late. So I would put it up once again on the chat box. Also, the YouTube channel goes by my name, Prasad Radhika. So if you put in Prasad Radhika, you would get the link to my channel. Still, some of you have not answered the poll. I strongly recommend that all of you answer the poll, only then I would proceed. It's good to attempt the questions first beforehand before looking at the solutions. I will definitely provide the solutions to all of you, but it's a good habit to first at least try solving it. And of course, if you get stuck, if you get the wrong answer, I'm here to clarify. Okay, so let us now discuss the answer. I see that quite a few of you are confused and not getting the correct option. I'm still waiting for that one question which everyone gets right, and I will be very happy that day. Okay, so the correct option in this is option C, sharper. And why is it so? So for that, we need to study the physics of Febry-Perot interferometer. Interferometer. And for that, let us draw it over here. So this is the Febry-Perot echelon. And let us say I have an incoming input beam like this. Let me draw the arrow. This is the incoming beam. So part of it gets reflected and part of it gets transmitted. Let me use a different color for the transmitted beam. So that's the transmitted beam. Again, at this second interface, part of it will get transmitted out and part of it will get reflected back again. And again, at this first interface, what you would see is part of it would get transmitted out and part of it would get reflected back again. And again, at this interface, part of it will get transmitted, and so on and so forth. We would have infinitely many such rays which are reflected and transmitted. Of course, the intensity would fall off with each successive reflection transmission by a factor of the reflection coefficient or the transmission coefficient. But for now, let us look at these many rays. So what we have is, we have this incoming E naught beam. The reflection would be E naught times R, where R is the reflection coefficient. Then it would get transmitted, so that would be E naught T. And then over here, this would be E naught T T prime, because this is transmission at the second surface. Okay, so let me write it down. So Febry-Perot is basically multiple beam interferometer. Why multiple beams? Because all these many beams that are there, reflection and transmission rays, which will be clubbed together and which interfere. So let me call this 1, medium 1, this is medium 2, and this is back again medium 1. This material is kept in such a way that the medium on the left and right are the same. So from interface 1 to 2, when the ray is in medium 1 and it is entering medium 2, so that 1 to 2 interface, for that we have the reflection coefficient as R and transmission coefficient as T. From 2 to 1, we have the reflection coefficient as R prime and transmission coefficient as T prime. So that's why this first ray is E naught R, and this over here would be E naught T. This is E naught T, and then when it comes out, it is 2 to 1 transmission, so that's why E naught T times T prime. So again, this would be E naught T, then E naught T R prime over here, and then T prime again. So this is E naught T, then R prime, this is reflection, this part, and then coming back out T prime. And then for this ray, it will be E naught T, then R prime, then another R prime, so R prime squared, and then T prime. So E naught T, T prime, R prime squared, and so on and so forth. This would continue. And this is the reflected beam, and ER, this is transmitted beam, ET. So we will combine all these infinitely many rays and they will interfere. Similarly for the transmission. So let me write down now for the reflection case first. So we have ER, which is nothing but E1R plus E2R plus E3R plus so on and so forth up until N, ENR, and then even more. Infinitely many rays would be there. So what are these? So the first reflected term is E naught times R. Second term is E naught T R prime T prime. And one more thing, there would be this phase difference that would be added. So this delta is 2 pi by lambda times path difference. Path difference is 2nd cos theta t. This we have seen previously. So this refractive index of this medium 2 is n, and theta t is this angle at which the ray is getting transmitted, this angle which is same as this angle. So this angle over here is theta t. And this thickness over here is d. Thickness of the material is d, and you can clearly see how this is coming. So the extra path, if you find out path difference between each successive reflected ray or each successive transmitted ray, would be 2nd cos theta t. That would give me a phase difference of 2 pi by lambda times 2nd cos theta t. This, if you have any doubts, you can watch the previous videos. There I have derived this particular path difference. Okay. Oh, and one more thing, this is just the amplitude. You would also have the time varying part. This is just the amplitude, and then time varying part, and then the phase difference that is added, the extra phase difference. Okay, let me shift this slightly upwards. I'm lacking space. And so on and so forth. This will continue. You can clearly see this pattern. Two n minus 3, this would be r prime to the power 2n minus 3. You can see and for delta it would be n minus 1, and so on and so forth. We can take some terms common. E naught e to the power I omega t. We can take common. Here also we can take this common. Stop me at any point if you feel this is going too fast or if you are missing some step. Feel free to ask in the chat box or just unmute and ask. Okay, so let me check the chat box if there are any queries. Oh, someone is asking what is E1R, E2R. Oh, this is just this. So this right here, this beam is E1R. This beam right here is E2R. And the next beam would be E3R and so on and so forth. And all of these would add up and interfere to give me the ER. I hope that clarifies. Okay, no more questions. Then we can proceed. Now this term right here, this in the square brackets, this term right here is an infinite geometric progression, infinite GP, with the first term as 1 and common ratio is r prime squared e to the power minus I delta. Now sum of an infinite GP is the first term divided by 1 minus the common ratio. And that's that. So plugging in this value, this gives me ER equals E naught e to the power I omega t R plus R prime t prime e to the power minus I delta over, because this term is there common, so and this times 1 divided by 1 minus R prime squared e to the power minus I delta. We can further simplify this. So we have from the principle of reversibility, again in the previous videos you can find this. So what we have from the principle of reversibility is that r prime equals minus r and t prime equals 1 minus r squared. So this comes from the concept that rays are reversible. So if you send in a ray from left to right, equivalently you can send it from right to left, and the ray would retrace its path. And also from the conservation of energy. So using these concepts, you can come up with these relations. And you can check it out in the previous video. We have derived it as well. Oh, wait. My screen got disconnected somehow. Are you able to see my screen? No, right? Yeah, people are saying no. I know that you're not able to see. Let me try and fix this. Okay, where is my screen? Why do I not see it? Sorry for this technical glitch. Please bear with me while I fix this. Yeah, okay. Still a problem. I thought I fixed it. Yeah, There you go. Now it's fixed. Great. Yeah, so I was talking about principle of reversibility, and from there you get these relations. And we can use these relations and plug it in over here to get the following form. So r prime becomes minus r, t prime is 1 minus r squared over 1 minus r prime is just r. Very good. Now simplify further. Let us take a common denominator. So this term gets cancelled out. Nice. Now the intensity is given as follows: half E star E. So let us find out the intensity. So this would be E naught squared by 2 R squared, then E star, right? So e to the power I omega t, and E star would be e to the power minus I omega t. So that term will cancel out. So first let me write E and then E star. So this is E times E star. One, let me just multiply this and open up the brackets. Okay, and this E naught squared by 2, this term right here, this we can write as I naught. So this is I naught 2 R squared 1 minus cos delta over 1 plus R to the power 4 minus 2 R squared cos delta. So this is the intensity for the reflected beam. Similarly, we can find out the intensity for the transmitted beam. Following the similar procedure, infinitely many transmitted beams. And just to clarify once again, this beam right here gives me E1t, this beam right here gives me E2t, and successive beams would be E3t, E4t, and so on. You can figure out this pattern by writing down uh like 5 rays. Maybe you will be able to see this pattern. Time varying term, and then more terms. Again, we will take some terms common. Once again, this is an infinite geometric progression with the first term equals to 1 and common ratio of r prime squared e to the power minus I delta. So sum of infinite GP is first term, which is 1 divided by 1 minus common ratio, which is r prime squared e to the power minus I delta. See, the common ratio is same as the previous case. So this gives me ET equals, let us put it over here, T prime over 1 minus r prime squared e to the power minus I delta. Again, intensity is IT, which is half ET star ET. This is E naught squared by 2. E to the power I omega t and e to the power minus I omega t, they cancel out. And in the numerator, we have T prime squared. Then let me write down for ET first. And then E star T. Let me open up the denominator. Once again, we will make use of the principle of reversibility relations. These relations over here. So Tt prime is 1 minus r squared and r prime is minus r. So here Tt prime, I will replace that with 1 minus r squared and square of that. In the denominator, I have 1 minus, this is r squared e to the power I delta, because r prime is minus r. Okay, so this gives me, again, this term I can call I naught. This term is I naught. The input intensity. I naught is the input intensity. Which is E naught squared by 2. So this is I naught and then we can use this e to the power I delta plus e to the power minus I delta is 2 cos delta. This is minus 2r squared cos delta plus r to the power 4. So this is my transmitted intensity. Okay, now we can see that if I do IR plus IT, then denominator is same for both. Numerator this is the numerator. If I expand it out, so this gives me 1 minus 2r squared cos delta plus r4, and you see numerator and denominator become equal. This gives me I naught, which it should be. From the conservation of energy, the input intensity should be sum of the reflected and the transmitted intensity. So input intensity is same as output intensity, and output consists of two parts, reflected and transmitted. But now we can write this reflected and transmitted intensities slightly differently by making use of some trigonometric identities. So we'll make use of the following trigonometric identity. So using this means 1 minus cos delta is 2 sine squared delta by 2. So using this trigonometric identity, we will write down IR and IT slightly differently. So IR okay, now we will use this identity. And now we will simplify it. Okay, correct me if I'm missing something because this is just algebraic steps. I can mess up over here. So we take this 2r over 1 minus r squared whole squared, this term common. So this gives me the following in the denominator. You will see why I'm taking this crazy looking term common. It's not as crazy as it appears. We will see the physical significance of this term. Similarly, for the transmitted beam, I know this question is turning out to be pretty long and time consuming, but once you get it, all the other questions will become very easy. So this is just the physics of Fabry-Perot interferometer. Once this is clear, you can solve any question on Fabry-Perot interferometer. So yeah, this is this. Okay, now you will see why I took that crazy term common. So now I define something which is known as coefficient of finesse. You see this term that I took common is the coefficient of finesse, and what this means that if I take the ratio of reflected to the incident intensity, then it comes out in this form of as a function of this coefficient of finesse and delta, the phase difference between successive beams. And similarly for the transmitted, the ratio and this term is basically given a special symbol A delta. So what happens is that for if you have higher value of f, then this gives sharper peaks, and higher value of f can be achieved by increasing r. So f is a function like this. So if you increase r, numerator increases, denominator decreases. As a result, the whole thing increases. So f can be increased by increasing r, which is nothing but the reflectivity, which is coefficient of reflection, means how much percent of the beam is getting reflected. So higher the reflectivity, higher the value of r, and higher the value of f, which means sharper peaks. So the question was, the transmission peak will become sharper if the reflectivity is increased. And let me draw some plots over here for you. So let me draw the axes. I'll try my best to draw. Okay, wait. Okay, this is probably the best that I can draw. Pardon me for my poor drawing. So this would be for, let's say, f equal to 1. This would be for, let's say, f equals, sorry, let's say this is 1. This is 0.2. And this would be roughly 200. And you can see that as my finesse increases, the peaks become sharper. What I mean by sharper is, if you look at this width, so over here for the pink one, the width is like this. For the red one, the width is like this. And for the purple one, the width is narrower. So narrower the width of the peak, sharper the peak is. And this is for IT over I naught, which is this airy function. It's called airy function. Airy function a theta. And this x-axis is my delta. And from here to here, from one peak to another peak, the delta changes by 2 pi. And this is, let's say, 0. This would be then 2 pi. And the dip is at 3 pi pi. So this is for the transmitted. What happens to the reflected? It would be the exact opposite because of conservation. So the reflected would be, if I were to draw, it would be just the exact opposite. Okay, how I don't want to draw it all over again. So what I will do is, I'll just interchange. And maybe I can try to copy this stuff out. And can I rotate this guy? Is that not an option? Sad. Can I not rotate? Okay, let me then delete and draw again. This would be the opposite of the transmitted part. This is f equals 0.2. This is f equals 1. This is f equals 200. And this number over here, this is 1. This is the origin with 0. This is 1. This is at 0. Okay, so, and this is such that we know that I r plus I t equals I naught. So the sum total of these two plots would be a flat line at 1. Okay, so I hope you understand now. This was super long. Again, you can see the sharpness in terms of the widths. So this width, red width is narrower, and the purple width is the narrowest. Sorry, the width is typically taken at full width at half maximum. So half maximum would be here maybe, or here. So half maximum at from the peak height to the peak minimum, peak maximum to peak minimum, you take that, and half midway of that, and then you take the width. Okay, so I hope this is clear. So someone is asking a question in the chat box. So yeah, so someone is asking about this reflected plot. So when the transmission peaks become sharper, then the reflecting dips become sharper. So this is a dip. This is not a peak. If you look at the peak, then you can say that this is a peak, but this is fat. And this part right here, this is a dip. This is a dip, and for here, this is a peak. So transmission peaks become sharper as reflectivity increases. Similarly, the reflecting dip becomes sharper as the reflectivity increases. Okay, so this finally brings us to the end of the first question. We can now proceed to the next question. This is also on Febvre-Perot interferometer. Oh, by the way, this plot never goes below the x-axis. I'm sorry. Let me erase this. Yeah, that's better. Hmm. Okay, moving on to the next question. Finesse of a Febvre-Perot interferometer is defined as option A, the difference of separation of adjacent maxima to half width. Option B, the difference of half of the of half width to separation of adjacent maxima. Option C, the ratio of separation of adjacent maxima to half width. Option D, the ratio of half width to separation of adjacent maxima. So I will refresh and relaunch the poll. Please take about a minute to answer. So I see that some of you have still not attempted the poll. Everyone, please do attempt the poll. It is for your benefit that you attempt the poll. It's always easy to just wait and look at the solution, right? But please do put in some effort to attempt the poll. Okay, so let me now discuss the answer. So separation between adjacent maxima, as you have seen, is 2 pi. Half width can be found out by equating this IT over I naught to half. So half equals 1 over. So add delta half by 2. So delta for which we find half width. This is basically nothing but IT over I naught. We are looking at this. We are trying to find out this half width. So this gives me, if I simplify, which implies delta half is 2 sine inverse 1 over square root f, and for large values of f this is small, and for small numbers we have this is approximately equals to 2 1 over root f. This is because sine theta is approximately equal to theta for small theta. Now finesse is defined as this 2 pi divided by 2 delta half, which is separation of adjacent maxima divided by full width, by 2 times the half width phase. So this is how it is related to coefficient of finesse. Notice that finesse is not the same as coefficient of finesse. So f over here is coefficient of finesse, and although they are proportional, they are not the same. So the correct option is option C, ratio of separation of adjacent maxima to the half width. Or rather it is kind of full width because it is 2 times the delta half. Okay, moving further to question number 3. For normal incidence, free spectral range is given by option A, lambda naught squared by 2, option B, lambda naught over 2 NFD, option C, 1 over 2 NFD. NF is the refractive index of the medium used. So these are the four options. I will relaunch the poll for all of you. Please take about a minute or two to answer. Oh, some of you have joined late, and some people are still asking for the YouTube link. Okay, I'll put it up once again on the chat box. Sorry. Okay, so let us now discuss the answer. So in order to solve this question, we need to know the concept called Rayleigh criterion. So when we have the peaks for two closely spaced wavelengths, so let's say okay, let me try to draw the neatest possible peak that I can possibly draw. Let's see. Let's try a few times. Okay, this third one maybe looks better. I'll use that. So let us say this is the peak of 1 and oh sorry, this is the second peak. Let me change its color. Okay, so these are peaks for two closely spaced peaks, and this distance between the peaks is delta. And if I do the sum total, like if I add them up, then I'm going to come up with a sum which looks something like this. Okay, this is my neatest possible attempt. So this so this is 1, and this point where there is dip, if this point is at 8 over pi squared, then we say that we are just able to resolve. So this is the Rayleigh criterion. This is from Rayleigh criterion, which comes up when we are looking at resolving two closely spaced wavelengths. And when this is 8 over pi squared, the location of the dip, then we say that we are just able to resolve. Okay. And if it is lower, then we are definitely able to resolve very nicely. If the dip is at 0, if it comes all the way down, over here, then that is the best possible resolution. And if it is less and if it is greater than 8 by pi squared, then that means we are not able to resolve. If the dip is coming over here, then we are not able to resolve. So greater than 8 by pi squared, if that is the location of dip, not able to resolve. Less than 8 by pi squared, if that is the location of the dip, we are able to resolve perfectly, like very nicely. Dip at location 0, perfect resolution. At 8 by pi squared, that means just able to resolve. Okay. Now, for normal incidence, if we have normal incidence, then in that case, theta t equals 0. This theta t over here that I had drawn, the angle of transmission, this theta t would be equal to 0 for normal, if the ray is just hitting the surface normally. So if we have m lambda naught, is the path difference between successive beams, if that is an integral multiple of lambda naught, and if theta t equals to 0, then we have the cos theta t is 1. This gives me m is 2 nd over lambda naught. So if I differentiate, this also gives me, upon differentiating, if I kind of differentiate, then I get m delta lambda naught plus lambda naught delta m equals 0, because this right hand side is a constant. This term right here is a constant. D is constant, refractive index is constant, thickness D is constant. So that is, differential of a constant is 0. So you get these relations, and from here I can get the following. Now, if my delta goes to delta plus 2 pi, then correspondingly my m, the order, will go from m to m plus 1. So this means that 2 pi over this delta of delta is 1 over delta m. Okay, because change in 2 pi in delta corresponds to change in 1 in m. So 2 pi change for delta is 1 change for m. Now what I will do is I will combine these two. Combining these two gives me lambda naught over delta lambda naught I just replaced this 1 by delta m with 2 pi over delta of delta and took the mod of it. So it just ignored the minus sign. It just denotes the change, the direction of change. So when the mth order peak for lambda naught overlaps with the m plus 1th order for the smaller wavelength for lambda naught minus delta lambda naught FSR for free spectral range, then this gives us the free spectral range. So let us now use our relations. And this delta of delta would be 2 pi from one peak to another peak. And lambda naught over m, from here we will get so the correct option is option D, lambda naught squared by 2 NFD. Okay, I hope this is clear. Let me check the YouTube chat box as well as the Zoom chat box once. Okay, I don't see any questions right now. So that means we can continue. That means either no one is paying attention or everyone is getting everything. Everyone is fully attentive. But anyway, we can proceed further. Let us move ahead. Question number 4. Now we have some questions on coherence length and coherence time. The coherence length of a source with coherence time 10 to the power minus 6 seconds is, this is a very simple question. Option A, 300 meters. Option B, 3 meters. Option C, 100 meters. Option D, 1 meter. So please take about a minute to answer. Oh, sorry. Another technical glitch or what? Okay, fine. Okay, so let us now discuss the answer. The coherence time is given to us as 10 to the power minus 6 seconds. So the coherence length is c times tc Pretty simple, straightforward question to calculate the coherence length given the coherence time. So, the concept of coherence length and coherence time, this comes up because when there is a source of light emitting light wave, it need not be just a single sinusoid. It could be in pulses. It could be like wave trains. And each successive pulse or wave train might not really be having the same phase profile or correlation between the phase for successive wave trains. They might just fall off the phase relation between these. So the coherence time tells you within what time will these pulses or wave trains remain coherent, meaning they would have a fixed phase relation between them. So within 300 meters, we would have no issue at all for trying to study any kind of interference effects. We would see perfect interference effects if we were to perform any interference effect with this particular source that we have. For example, if you want to use this laser in a Mach-Zehnder interferometer, or a Michelson interferometer, we have studied Michelson interferometer. Then up to a path difference of 300 meters, you would see perfect interference fringes. Beyond 300 meters, if the path difference exceeds 300 meters, then the fringe visibility would start falling down. So this is the significance of coherence length and coherence time. Oh yeah, coherence time, that means within that time frame, if you study any temporal interference effects like Mach-Zehnder interferometer, if the time difference is 10 to the power minus 6 seconds, you would be able to see good interference effect, good visibility. Okay, so now we can move to the next question. Coherence time of a source with bandwidth delta nu equals 10 to the power 12 hertz is option A of the order of 10 to the power minus 8 seconds, option B of the order of 10 to the power minus 10 seconds, option C of the order of 10 to the power minus 12 seconds, or option D of the order of 10 to the power minus 6 seconds. Again, a pretty simple and straightforward question. Please take a few minutes to answer. So we are halfway through now. This is question number 5. 10 questions every week. So 5 questions done, 5 more to go. Okay, so let us discuss the answer. So delta, oh, let me change the color of my pen. Delta nu is of the order of 1 over the tau c, the coherence time, which implies the coherence time is approximately 1 over delta nu. Delta nu is this bandwidth. So this is 1 over 10 to the power 12 hertz, which is 10 to the power minus 12 seconds. Hertz is 1 over seconds. Pretty simple and straightforward question. So I hope these two questions on coherence time and coherence length are clear. You would get such simple questions in your quiz and assignment as well. Simple numericals where you find out the coherence length given coherence time or the bandwidth from the coherence time, stuff like this. Okay, I'll check the YouTube forum once again. Okay, no question, so we can proceed. Relative intensity transmittance of a Fabry-Pérot interferometer is option A. Okay, so these are the options. We discussed Fabry-Pérot interferometer in the very first question of today's assignment. So you could go back and review that question before coming to answer this question. Okay, I think I forgot to relaunch the poll. Let me refresh and relaunch the poll. Oh, sorry. Yeah. Okay, so let us discuss the answer. The correct option is option A. And let me recap what we studied in the first question of this week. So we derived the intensity for reflected and transmitted parts for a Fabry-Pérot interferometer. And the Fabry-Pérot interferometer is based on the concept of multiple beam interferometer. So why multiple beams? Because you have multiple reflected beams which combine to give a reflected part, and multiple transmitted rays which combine to give one transmitted part. And finding out the intensities for these reflected and transmitted parts, we finally figured out the ratio of the uh, reflected and transmitted intensities with respect to the input intensity. And this is what we came up with. These were the final expressions. Let me highlight them for you. So, okay, let me. Yeah, so these were the final expressions. And this over here is 1 minus Airy function, which it should be from conservation of energy. So these are the expressions, and we were told to find out to basically select the correct option for relative intensity transmittance, which is nothing but this. Okay, so let me come back. And this term over here is for reflectance. That is IR over I naught, and this is IT over I naught. Okay, next question. Again on Fabry-Pérot interferometer, one can improve finesse of a Fabry-Pérot interferometer by option A, increasing reflectivity of the mirrors, option B, decreasing reflectivity of the mirrors, option C, not changing anything, and option D, none of these. Again, a similar question we had seen earlier in the first question of this assignment, and please feel free to revisit that question and answer this question. Okay, so let us now discuss the answer. So as discussed earlier, I had shown earlier that finesse is different from coefficient of finesse. This is finesse and this is coefficient of finesse, and this is the relation. So let me write it over here again. So finesse is equal to pi root f by 2, where f is coefficient of finesse and f is in turn 2r over 1 minus r squared whole squared. This was seen in the first question. Where is it? Yes, over here, this coefficient of finesse. And r is nothing but reflectivity of mirrors, means the it's the reflecting coefficient, reflection coefficient. So if I, in order to increase my finesse increases by increasing my coefficient of finesse. This will happen when my r increases, the reflection coefficient, because if r increases, then the numerator will increase and the denominator decreases, which means that the overall thing, overall ratio increases. So, and r is the reflection coefficient, and to increase that you have to increase reflectivity. Okay, and since finesse and coefficient of finesse are linearly proportional to each other, so if there is some way I can increase my coefficient of finesse, then that same method would work to increase my finesse as well, because of this linear relation, because of this proportionality. Okay, great. Moving on. Coefficient of finesse for a Fabry-Pérot interferometer is 100. The value of the ratio delta lambda naught FSR, this is the free spectral range, over delta lambda naught min, will be option A 14, option B 15.7, option C 14.6, or option D 18. This is a pretty simple, straightforward numerical. I have refreshed and relaunched the poll for all of you. Oh, sorry, I should not be moving it. Yeah, here is the question. Okay, so let us now discuss the answer. This ratio over here is nothing but finesse. This is equal to finesse, which is pi root f by 2, where f is the coefficient of finesse, which is 100. So this is equal to pi root 100 by 2, which is 10 pi by 2, sorry, 10 pi by 2, which is 5 times pi. And let me pull out my calculator. 5 times pi. Okay, so this is approximately equal to 15.7. Nice. So moving on. Any question up until now? Let me once again check my Zoom chat and YouTube chat. Okay, so let us move ahead. Two more questions to go. Question 9. The minima of a Fabry-Pérot interferometer sorry, not the minima, the mirrors of a Fabry-Pérot interferometer have an amplitude reflection coefficient of r equals 0.9, then the coefficient of finesse is option A 45.65, option B 76.80, option D 89.75, or option D 50. So take about a minute to answer the poll for this particular question. Okay, let us now discuss the answer. So, as discussed in the first question, this is the expression for coefficient of finesse. So, let us come down and let us write it over here once again. So, coefficient of finesse is given like this. And we are given the value of r, so we just need to plug in. I need to bring out my calculator. So my calculator tells me, let me plug this in the calculator. 1.8 divided by, this is approximately 89.75. Great, option C. Very simple, straightforward questions. You will definitely get such some questions which are simple, straightforward numericals. You have to just remember the expressions. Okay, last question for the day. The mirrors of a Fabry-Pérot interferometer have coefficient of finesse 64. The half width is option A 0.2, option B 0.9, option C 0.8, or option C 0.5. So I will restart the poll one last time for the day. Yeah, it is active now. Okay, let us now discuss the answer. So the expression for half width, we had discussed this earlier somewhere. Where? Yeah, here. This is the expression for half width. We will make use of this. So delta half is 2 over root f. I believe that's the expression. Yeah, 2 over root f. And we are given f is 64, 2 over root 64, which is 2 over 8, which is 1 over 4, which is 0.25. But, okay, wait. This is the width, sorry. This is the full width. 2 times delta half will be the half width. This is just the phase, means this is just the delta for which there is, we get the half width. So this is 4 over root f, which is 2 into 0.25, which is 0.5. Option D. So this brings us to the end of week 6, and we are halfway through. 6 more weeks to go. And once again, I will put up the link to the YouTube channel in the description for everyone. Okay, thank you very much. Yeah, thank you everyone for coming over here. Okay, see you next week, next Saturday. Saturday at 3 p.m. Okay, bye.